Hey guys, I'm going to go over how to graph the other kind of rational equations now. These are the kinds that have just one fraction on them, and there's not really any transformations involved. It's just kind of memorizing the rules and how to go about it. So I'll do that. I just want to, on a side note here, this is my absolute favorite lesson to teach. I love this lesson. It's so cool how these graphs end up turning out. And it's killing me that I'm not going to be able to be there with you guys to go over these with you and show these in person. So I just wanted to put that out there. So let me go ahead and pull this up and we'll talk about this now. All right. Now, first thing I want to mention is don't get freaked out about all this right here, okay? I'm going to explain that real quick in a very simple diagram. All right? How many of you guys remember remember what the degree of a polynomial is? The degree of a polynomial, remember, is the largest exponent on the polynomial. Okay? And so what we have here is we're talking about fractions or functions that have a fraction, and we're looking at the degree of the numerator and the degree of the denominator, okay, m and n, okay, the largest exponent. And when we have equations that are fractions like this, we can have three different situations. One is where the degree of the numerator is less than the denominator, so it's m is less than n. So an example of that would be something like y equals x plus 2 over x squared minus 1 would be an example of that one. That's a case where the degree in the degree in the numerator on here is 1, the degree in the denominator is 2, so m is less than 2, or m is less than n here, so that is our first situation. The second situation is where the degrees are equal. So if I have something like y equals x squared plus 3x plus 2 over x squared minus 6x plus 5 be an example of that. Okay? And that's where our degrees are the same. They're both second degree, x squared over x squared, so the n equals n. And then the third one is where we could have something like y equals x to the third plus 6x plus 5 over x squared minus 4x. I'm just making this up off the top of my head here. Okay? And this is where our degree is greater in the numerator than in the denominator, because it's third degree over second degree. Now, in this class, in Algebra 2, we have never worried about these. These have really special graphs that we just don't deal with in this class. Advanced Algebra 2 does, and if you go on and take college algebra next year with KU, you'll deal with those next year. This year we are just dealing with these two situations, when our degree is less in the numerator than in the denominator, and when our degrees are equal. And so let's take a look at the first one. The first one is the degree in the numerator is less than the degree in the denominator. And so the different things we're going to have to figure out is horizontal asymptote, vertical asymptote, and I'm going to put a little parentheses S on it because we could have more than one vertical asymptote. We can find our x-intercept, and I'm going to put a little S on that one as well because you can have more than one x-intercept. And the y-intercept, and you can only have one y-intercept. You could have 0, but you can't have more than one. All right, so horizontal asymptote. When our degrees our degree in our numerator is less than the degree in the denominator, our horizontal asymptote every single time is going to be the line y equals 0. Every time, no matter what. The reason that is because horizontal asymptotes are measures of end behavior. In other words, when x is really, really, really big, or when x is really, really, really small, meaning positive infinity or negative infinity. So if I take a look at this example that I wrote up here, if x is infinity, then I'm going to have infinity plus 2 over infinity squared minus 1. That's when it's really big. And no matter what I do, it's always going to be a number that is, the numerator is always going to be just a little bit above 0 every time when I divide those. It's always going to be just a little bit above 0. Or if it's negative infinity, it's always going to be just a little bit below 0 every single time, no matter what. It's never going to equal 0, but it's always going to be really, really close to 0. Okay, so our horizontal asymptote's always going to be y equals 0. Our vertical asymptotes, that is any value of x that makes the denominator equal to 0. So we're going to set the denominator equal to 0 and solve it. Sometimes we'll have 1, sometimes we'll have 2, sometimes we could have 3, you could have, however, whatever your degree is in your denominator, that's how many vertical asymptotes you could have. Our x-intercept. Our x-intercept, or intercepts, we set the numerator equal to 0 and solve it. That'll give you your x-intercept. And the y-intercept, plug in 0 for x and solve. Okay? Those are our rules on how to find those particular terms, and we'll go through some examples of this. Okay? Our second possibility is when our degrees are equal. Okay, in this case, we've got a second degree over a second degree, so our degrees are equal. And you'll recognize that the only thing that is different is the horizontal asymptote. Everything else is the same. To find the horizontal asymptote when our degrees are equal, it is the fraction of the leading coefficient over leading coefficient. So in the example that I have up here, my leading coefficient is 1, leading coefficient is 1, and so the horizontal asymptote on that graph would be the line y equals 1. Okay? If it was 2 over 1, the horizontal asymptote would be 2. If it was 1 over 3, it would be 1/3, and so on. Okay? It's leading coefficient over the leading coefficient. And everything else is exactly the same. Okay? The only difference between these two is the horizontal asymptote. Everything else is exactly the same. So let's look at some examples now using these same rules. First one, I've got the equation y equals 2x squared over x squared minus 9. First thing we want to do is we want to identify the asymptotes. Horizontal asymptotes, vertical asymptotes. Okay? So in order to do the horizontal asymptote, we need to determine the degrees. The degree in my numerator here is 2. The degree in my denominator is 2. And so it is the same degree. And so it is leading, so my horizontal asymptote is going to be leading coefficient over leading coefficient. Leading coefficient is, on my numerator is 2, leading coefficient, my denominator is 1, And so my horizontal asymptote is the line y equals 2. And so over here on my graph, along y equals 2, I'm going to put a dotted line. That's my horizontal asymptote. Right along there like that. Vertical asymptotes. This is where we set the denominator equal to 0. So I say x squared minus 9 equals 0. Then I solve that. I could factor x squared minus 9 to x plus 3 times x minus 3, or I could just say x squared is equal to 9 by adding 9 to both sides, and then take the square root. X is equal to positive or negative 3. And so my vertical asymptote is the line x equals 3 and x equals negative 3. So along x equals 3 and x equals negative 3, I'm going to put a dotted line for my asymptote. Okay. So vertical asymptote is x equals 3 and negative 3. Horizontal asymptote is the line y equals 2. X-intercept. X-intercept, remember, is when you set the numerator equal to 0. So x-intercept, set the numerator equal to 0. 2x squared equals 0, divide by 2. So take the square root. I get x equals 0. So my x-intercept is going to be the coordinate 0, 0. Okay, because on your x-intercept, y is always 0. So there's my x-intercept, 0, 0. The y-intercept, that is where I plug 0 in for x. Excuse me. Plug 0 in for x. So that's going to be 2 times 0 squared over 0 squared minus 9. That all comes out to 0. So 0, 0 is also my y-intercept, which makes sense, because that is also on my y-axis right there. Okay? To find other points and where the rest of this curve goes, use Desmos. Okay? Make a table. You can plug values in, but use Desmos, because that will kind of show you what the curve looks like. So I'm going to go ahead and pull up Desmos. And I've already got this one entered for us. Right here. And see all those curves go? Okay. It looks like I've got a curve that, notice the horizontal asymptote is at 2. And then I've got a vertical asymptote at negative 3. I've got a vertical asymptote at positive 3. And notice how the curve goes downward in the middle and it goes upward on the sides. And so if I pull this back up, I've got the curve then that goes like this. Then I had another curve that went like this. And then another one that went like this. And if you want more exact points, you can start plugging some values in. But for our purposes, we can just use Desmos and kind of get an idea where these curves go. Last part on here is domain. We don't worry about range on these so much because range is a little more tricky than this. But domain is something we can certainly take a look at and figure that out pretty easily. We've got 3 different regions here. We've got one region that is where x is less than negative 3. We've got one region where x is between negative 3 and positive 3. And we've got a third region where x is greater than 3. So our domain is going to go from negative infinity to 3, and then from 3, to negative 3, and then from negative 3 to 3, and then 3 to positive infinity. Okay? And that is the gist of what we're going to be doing today, right there. I've got a couple more examples. I'm going to go through them a little quicker than what I did this one, because I don't want this video to last too terribly long. So let's take a look at this one. Again, we have m over n is going to be 2 over 2, so our degrees are the same. Okay, same degree. And so that tells me that my horizontal asymptote is going to be leading coefficient over leading coefficient, or 1 over 1, which is 1. Right there. To find the vertical asymptote, I need to do a little work on this, because x squared plus 3x plus 2 and x squared minus 4, that all factors. And so I'm going to factor all this, because what we're going to find here is this one's kind of special. X squared plus 3x plus 2, that factors to x plus 2 times x plus 1. And x squared minus 4, that factors to x plus 2 times x minus 2. Notice we have x plus 2 over x plus 2, which cancels. And so what we have left over is x plus 1 over x minus 2. The curve we draw is actually going to look like that curve right there. But we have something special in this one. Because our x plus 2 over x minus 2 is in my denominator, I know that x cannot equal negative 2 or positive 2, right? Because that would make 0 in my denominator. Now, because the plus 2's cancel, my vertical asymptote is only going to be the positive 2. Okay? Positive 2 is my vertical asymptote. I can't do anything about that. But because the x plus 2's cancel, that doesn't make an asymptote at x plus 2. What that actually does is that makes what we call a hole in the graph at x equals negative 2. Okay, so our vertical asymptote is going to be x equals 2. Let's go ahead and write that in. Okay, a hole in the graph now is going to be at x equals negative 2. And to determine where the coordinate is of the hole, I take x equals negative 2 and I plug it into this equation over here now. And so it becomes negative 2 plus 1 over negative 2 minus 2, which is negative 1 over negative 4, which is 1/4. And so our hole is going to be at the coordinate negative 2, 1/4. So negative 2, 1/4, right here is going to be a hole right there at that graph. Now to find some other points, I can use the x-intercept, y-intercept. The x-intercept, remember, is when you plug in, or when you set the numerator equal to 0. And so if I set x plus 1 equal to 0, then that gives me x equals negative 1. So negative 1, 0 is going to be x-intercept right there. And then the y-intercept, that's when I plug in 0 for x. If I plug in 0 for x up in this equation up here, then that tells that's going to be 0 plus 1 over 0 minus 2, which is negative 1/2. And so I'll get 0, negative 1/2 is my x-intercept, or my y-intercept, sorry, which is right there. So this curve here is going to look like this. It goes through here, then here, and it jumps down here, with that hole at negative 1, or at negative 2, negative 2, positive 1/4. There's that hole right here. Okay? And then the other part of the curve, I need to plug in some values that are bigger than 2 for this other side over here. And I already made this up on Desmos, and so I'm going to go ahead and just kind of pull that up and show you what it looks like. See how it looks right there? Okay, and the Desmos doesn't really do a good job of showing this, but at negative 2, 1/4, there should be a hole right there. Okay? All right. And then for domain, we only have two regions here. We've got a region from, sorry, we actually have three regions because x can't be -2, right? So our domain is still going to be -infinity to -2 because it can't equal -2. Then it goes from -2 to +2. And then it goes from 2 to positive infinity. Okay. And I've got one more example with you, and I just wanted to go through this one again really quick just so you can kind of see a problem or a graph that looks like this. This one is one of the more, I guess, funky looking ones. Here I've got my numerator degree is less than my denominator degree, right? Because this is degree 1 and this is degree 2. And remember, in that situation, that was the first one we had here, where our horizontal asymptote is y equals 0. So we have a horizontal asymptote at y equals 0. Vertical asymptotes, x squared plus 3x equals 0. Solve this for x by factoring out x. And so I get x equals 0 and x equals -3. So I've got two vertical asymptotes at 0 and at -3. Okay, so there's no holes in this. And now to get the rest of my points, I'm just going to put this on Desmos so you can kind of see what this thing looks like. I'll pull that back up. That is this one right here. Everybody see how that one looks? We've got that vertical asymptote at 3. We've got the vertical asymptote at -2 or at 0. And then we've got a curve in the lower left. We have a curve in the upper right. And then the curve in the middle actually goes through the horizontal asymptote. Okay, so it looks like this. There's the curve down here. There's the curve up here. And then this one goes through the asymptote right there. Okay? I wanted to show you one like this because horizontal asymptotes in the middle can actually have curves that go through them and touch them. Okay? Horizontal asymptotes are indicators of end behavior. Notice on the ends out here, it approaches the asymptote. Over here, it approaches the asymptote. In the middle, in here, it can touch the asymptote. So don't be surprised if you come across any equations like that where that can happen. Okay? So I just wanted to show you one like that so you've seen that. Okay? So I'm going to go ahead and stop the video now. I will be available in Zoom meetings at our regular times. And I'm going to go ahead and post the mastery quiz along with this video and practice problems. So please feel free to reach out if you have questions. And everybody have a great day. And please, please, please stay healthy.